How do you like what I have so far? Is that something like what you have? We found the standard cell potential. We got 2 for the end value. And now we have to fill in what the concentrations are. What is the concentration of the hydrogen ion? This thing right here. Look at this right here. Use a different color. The problem says it's the standard hydrogen electrode. That tells you what its concentration is in standard conditions. It's 1 molarity. And that hydrogen gas is at 1 atmosphere. And the copper, though, is not in standard conditions. It tells you up here the copper ion concentration is 2.5 times 10 to the negative 4th. Yeah. Those are our concentrations. That's what we plug in. Now, by the way, with gases, you should include the pressure of gases with the concentrations when you're finding Q. Most of the time, though, the gases are going to be at 1 atmosphere. Probably all the time they'll be at 1 atmosphere. So just know that they're part of it, too. The Q has all the dispersed states of matter, which would be gases and aqueous. So anyway, this would be 1 squared over 2.5 times 10 to the negative 4th. I don't have room to multiply it by 1. So we'll just go like that. Now, is this reaction, at this point in the reaction, is it reactant heavy or product heavy? Look carefully. Is it reactant heavy or product heavy? It's product heavy. Yeah. It is. Because we have a tiny little concentration of this reactant. And we have 1 molarity for our product. So this thing is definitely product heavy. It's reactant light. And do you remember what we talked about yesterday? What does that do to the voltage if the reaction is product heavy? It's still spontaneous this way, but what? It's lower. It's not as high. And the lower the reactants go, the less voltage you're going to get. So when we crank this out, I'm expecting something lower than the standard cell potential because we are less than standard conditions now on the reactants. What do you get? Anybody get an answer for it? 0.23. 0.23 volts. Yep. Just pausing. Is there anything that I can answer about this? Go ahead.
Wait, how do you know how it's set up?
This thing right here? Well, see, it never gave us a chemical equation. It said we have a cell. It consists of a standard hydrogen electrode. So they're expecting you to know that a standard hydrogen electrode means this. Hydrogen ions change into hydrogen gas. There's no other half reaction in the table that will lend itself to a standard hydrogen electrode more than this would. And then it says a copper metal electrode. Now, the Zumwalls are expecting that you're going to know a copper metal electrode has copper positive 2 changed to copper neutral. Why does it expect you to know that? I'll just tell you that positive 2 oxidation state of copper is by far the most common. I know that on the table is copper plus 1 yields copper. If I gave you this on a test, you could definitely argue, hey, how am I supposed to know that it's copper 2 and not copper 1? And that would be a valid argument. But now I'm going to tell you that when I tell you when I have copper metal electrode, you got to know that copper 2 is more common. I wouldn't give you that anyway. I would give you, if it were a test, I'd give you the chemical equation. But the Zumwalls, you know, they leave stuff out there. They give you just enough sometimes to be able to figure it out. So anyway, when you had these 2 half reactions, and you know it had to be copper 2, they're both written as reduction, so one of them has to be turned around. You need to turn one of them around, which makes it negative, but you still have to be able to add them together to get a positive number. So it had to be that one that was turned around. Okay? Yes?
And you can manipulate the hydrogen ion concentration of that, like the 2H plus?
It said standard. So that means that it had to be at standard conditions, 1 molarity. Now, is that the 2 that's bothering you? if it weren't standard, then they would have to tell you what the concentration is.
I think about like in lab terms, like is that like do you add a certain amount of each kind, like can you control how much hydrogen you have?
Yeah, you would have to. You'd have to have a carefully measured 1.0 molarity acid solution. Yeah. Yep. Okay, I want to show you one more example, but I don't want to do the problem. I just want to make a few comments about it. The next example is another one in the book. Let's just take a look at it. An electrochemical cell consists of a standard hydrogen electrode. Oh, we've seen that before. And a copper metal electrode. Oh, good. Okay. So it turns out to be the same reaction as the last one. But then it goes downhill. If the copper electrode is placed in a solution of 0.1 molar sodium hydroxide that is saturated with copper hydroxide, what is the cell potential then at 25 degrees? Then they give you a KSP value, copper hydroxide. This problem is obnoxious. I look at this and I think, man, the Zundals must have had a bad day. When they gave you this, they were angry about something. And they were passing off that misery onto you. Can I at least show you how you would set this down? When you look at this, what in the world? We were doing okay with the first statement there. Oh, standard hydrogen electrode, I know what that is. Ah, copper metal electrode, I know what that is. So I already know that the chemical equation is this one right here. So, man, we're doing good so far. Standard cell potential is right there. But then they go into this sodium hydroxide and copper hydroxide and KSP. What? Well, here's what they're doing. The standard hydrogen electrode means that the hydrogen concentration is 1. The hydrogen gas pressure is 1 atmosphere. That's standard. That information they gave you in that second paragraph was all about finding the copper ion concentration. Yes? So, not only did they give you something that's not very soluble and say, okay, well, you got some copper hydroxide dissolved. Not only did they do that, but the copper hydroxide was not in pure water. It's in a 0.1 molar sodium hydroxide solution. So they're being rotten on this one. Here's what you would do. Because we're given the KSP, copper hydroxide, we don't have an initial concentration of it because it's not very soluble. So we have to use what we learned in chapter 16. Chapter 16, the solubility. We just did that one. Yeah, it's got to be this. We got copper plus 2 and 2 hydroxides. That's how it would, and we're going to need one of these. Initially, it says do we have a saturated copper hydroxide solution, so that's a solid. Initially, before that was dissolved, there was no copper, but the hydroxide, there was an initial concentration. That's what we call the common ion effect. I've talked about the common ion effect. When you have already one of your products there, and this thing is trying to dissolve, it's not going to be able to dissolve as much because you have an initial concentration of something. So this is going to dissolve. It's going to go down by x and up by x and up by 2x. There's the 2 there. And then in equilibrium, that's x and that's 0.1 plus 2x. So you know the KSP values. KSP equals that times that squared. You'll be able to cancel out one of those. Which one can you neglect? The x term, yeah. Because you know that x is small. There's a tiny k value. So x is really small. When you get that x, that's the copper concentration. You put it in for that. Oh, man. What a nasty, rotten problem that is. Do you think that, or is that a nice problem to you? Felix, would you enjoy doing that problem? No comment? I couldn't believe when I saw that. Now, that may be one of the assigned problems. I just saw it and grabbed it. Mr. Hevel normally does the assigning of problem. And I said, okay, that looks good to me. So if you come across this problem, you have to do all that. Now, as I go through that, I know that you're thinking, oh yeah, we know how to do that. But at first, getting started on that is dreadful, isn't it? Would you have known to do that? Well, I don't know. But yeah, we have that. All right. I have just one other thing for you before we start the last topic of the chapter. Equilibrium constants. I know. I thought we were done with equilibrium constants. Weren't we? Didn't I promise that we were done after 4 chapters? But then we have this. Well, I'm just letting you down gently from equilibrium. If we stop cold turkey, that's when you get the night sweats and terrors, you wake up screaming. So we have to just phase out the equilibrium. All right. I do have to tell you this, that electrochemical reactions, they start out like crazy. They are making products, and you got this nice big voltage, and as the reaction happens, the voltage goes down. As the reaction happens, eventually we're going to get to the point where it stops. The reaction will have 0 voltage. And that's equilibrium. We've learned that. We've done that a lot. The point at which the reaction stops, there'll still be reactants there, but it's not happening anymore. So at that point, the Q value, the status of the reaction, is now K. Because the reaction stopped. And remember, K is the ratio of products to reactants at equilibrium when the reaction stops. So because of that, if no current is flowing, that means that the cell potential is 0. Because if the cell potential weren't 0, you'd still have current flowing. Now all we would have to do is plug this into the Nernst equation. The Nernst equation says the cell potential equals the standard cell potential minus 0.0591 over n log of Q. But in this case, that term right there is 0, because the reaction stopped. And it's at equilibrium, therefore Q equals K. So you would be able to solve for the K by just taking that expression and getting K by itself. So that leaves us with, if I rearrange the thing just to solve, this case it's solving for the log of K. All you got to do though is do the algebra here and move this whole term over to that side and then solve it for log of K. And you'd have that. Now honestly, I don't recommend, because I know how my brain works, I would not be crazy about trying to memorize this equation to solve for the equilibrium constant. I'm totally fine remembering the Nernst equation and just plugging 0 into that. Because that's all that's happening here. Now I know that there was a Q and now it's a K, but since it's at equilibrium, you just change Q into K. And solve for K. But yeah, so you sometimes, there's only a couple of problems that will be like this in the exercise. This is not a major part. I don't even have an example problem for you because it's simple. These are not going to be difficult problems. I would say that you should have a sense of whether K for an electrochemical reaction should be big or small. In general, what do you think K is for an electrochemical reaction? Is it big or small? Why? Aren't the reactions spontaneous? Don't you have to have a reaction that's spontaneous for a galvanic cell? You want to change your answer on small? If it's a spontaneous reaction, I would guess that K would be big. Yep. And if you just look at this, you're going to have N, which is a whole number, positive whole number, times the cell potential, even if that's a small number, it's being divided by 0.05. And then it's got to be raised to the power on 10. Ooh, man. So K is going to be big. All right. So